Okay, I'm now sharing the screen. And let me go to the notes. Okay.
So can you turn off your video?
Yeah, yes, that's better, I think. Yes, I'll do that out. Right. Okay. So you are all you are able to look at the notes here. I
Yes,
hope.
sir.
Yeah, good. Just let me keep this link also aside. Okay. All right. Uh, the last but one lecture was on discrete time processing of continuous time signal. This I hope most of you would have gone through it. The scenario here is you might be having initially a continuous time signal, but most of the time these days you would do discrete time processing of those signals only. The very simple example is what we are now talking in this call. Like for example, the audio originally is a continuous time signal, right? The pressure varying continuously, the sound from coming from the sound waves, and then what you are hearing at the end is also a continuous time signal, but in between the processing is a discrete time processing, right? So I have put, if you have noticed in the presentation, I have put some block diagram of your DSP kits also. It's not exactly the complete block diagram of your the exactly that kit, but overall it serves the purpose. So basically there you would be having a mic in which has a continuous time signal. Then there you have a something called as a codec, which is used for conversion of analog to digital and digital to analog signal. So that essentially would be converting that signal to a discrete time signal. And then you do the whatever processing you want to do is you would be doing using the discrete time system. And after that, depending on the application and the purpose, you would be sometimes would be again going back to codec. Suppose if you are listening to the audio, then you would again go back to the codec and you get the output after converting from discrete to analog signal, right? This is the overall flow, and that should give us the context on why this is important. Okay, so here we would be, particularly in this video, we will be taking a look at a couple of aspects very specifically. One of them is this continuous time signal. So effectively you have, if you treat the whole thing as one box here, okay, from getting xc of t as, okay, let me just see if I could get a pen here. Hopefully, yes, we were doing it earlier. Okay, yeah, not the pen, but the spotlight. Yeah, right. So if you look at the whole thing put together, you have as an input here x. Oh, it is not coming below that. Okay, right. So hopefully I should spotlight. Okay, so if you take this as an input and the other as the output here, right, which is also a continuous time signal, you could notice there that, okay. So you could notice that you could treat as if the whole thing is a continuous time signal. So that what is it exactly doing? This is H effective of j omega is what we would like to look at. And is this always an LTI system? So if you recollect the properties of convolution and then followed by its equivalent properties in the frequency time domain, you could realize that if your output is the frequency spectrum, the h of e power j, h of j omega times the frequency spectrum of your input, then that's an LTI system, right? So these are the two things we would be analyzing in this. Then we did an analog to digital conversion. This part, this is nothing but the first two lectures that we discussed, where you give as an input a continuous time signal, you get then as an output discrete time signal. And then this part is what you have studied in DTFT. Your input is x of n, your output is y of n, you are doing discrete time processing. And after that, the next part is what we have studied in the third video lecture of sampling, where you give as y of n, and you would like to reconstruct a continuous time signal. So these three modules, we already have the enough background. So we were writing simply the relationships in the time domain and the frequency domain for all these three blocks here. Okay, with this we have done, and then we simply then concatenated everything to get the relationship. Okay, before that, just let me put a brief like pause on HR of t. Okay, so this part, what did we see? This is equivalent to a reconstruction filter, right? Yeah, I have written HR of t, but this is digital to n, that is multiplication with an impulse train, the whole digital to analog converter where you have HR of t also. Okay, this is slightly inaccurate, but it's okay. So yr of t would be essentially equivalent to your y of n into shifted sinc functions, and this sinc is there at for every n, it is there at nt, this sinc is placed, and its equivalent response in the frequency domain is a low pass filter having this I am writing for not the shifted version, but the original HR of j omega, having cutoff frequencies at minus pi by t to plus pi by t. So this is t in that ratio, in that range of values. Okay. So then you HR of j omega, if you come from the other end and try to get back, you could express yr of j omega in terms of the input. That's what we have essentially done it here. Okay, you just keep on substituting the going output of the one module is the input to the other. So you go back from the right hand side to the left hand side. So this is what you would be ending up there, the relationship. This being the frequency spectrum is equal to, there are some terms here, HR of j omega, just now we discussed, is t for minus pi by t to plus pi by t. You could already notice here, because of this whole function value outside omega equal to minus pi by t to plus pi by t is going to be 0. Now the question would be, what would be the nature of the summation in the range of minus pi by t to plus pi by t? So as long as, so this pi by t, what exactly is that? So if you recollect, omega s is the sampling free. So this copies are getting placed at 2 pi by t into k, correct? So this copy you are placing at 2 pi by t, and your cutoff is at pi by t. So if at all there is any aliasing, this copy which you are placing at omega s would cross this boundary and come inside, and then this y of j omega equal to some frequency, some h of j omega into xc of j omega doesn't work out as such, because there are summation of multiple copies going on here beyond pi by t. So that's why this simple thing we are right now looking at is omega is equal to 2 pi by t. So what would happen when there is no aliasing thing? Okay, that's what we looked at. Then we were also substituting these values here. HR of j omega anyway is within this pi by t range. This is equal to t. Okay, we are in fact writing the expression now just for the interval of minus pi by t to plus pi by t. And anyway, the outside this yr of j omega is becoming 0, right? And then this is 1 by t term is there anyway. H of e power j omega t is there anyway. When there is no aliasing, this copies, multiple copies you are placing will not be there. Any of these copies in the summation will not be there from 0 to pi by t or minus pi by t to 0. Okay, so simply you have there xc of j omega. So what you had here is the frequency spectrum of the output is equal to the frequency spectrum of the input multiplied by h of e power j omega t, right? So this now assures us that this is an LTI system, and that effective frequency spectrum with respect to the continuous time domain is going to be h of e power j omega t. Very important result here. Okay, and then we discussed, yeah, as I mentioned, this is a sufficient conditions. Okay, sometimes what could happen is, because of the nature of h of e power j omega t that is there here, what could eventually happen is there could be specific instances where, despite having an overlap, you could still might not be having, still it behaves as an LTI filter, and you would be getting an appropriate output. Okay, that's anyway for specific cases. Okay, not the common thing. Okay. Now we looked at what would be the case for suppose you want to do a low pass filtering of your continuous time signal. What you are having is in your discrete time system. This is what you have under control, right? And then with this, you have to effectively achieve this for a continuous time signal, but you have the whole thing in the discrete time signal. So assume that your h of e power j omega equal to 1 for minus omega c to plus omega c. Okay, then what would be its equivalent h effective of j omega is the question. So you could see here h effective of j omega t is nothing but h of e power j omega t, isn't it? So which is omega. Now the cutoff frequencies would be equal to less than or equal to pi by t here. Okay, now omega c, this relationship we know, okay, omega into t equal to omega is again the relationship we got here, because h of e power j omega t is nothing but h of e power j omega computed at omega equal to omega t, isn't it? So what you get here is this. Now if you look at the effective continuous time frequency response, it acts as a still as a low pass filter, but the cutoff frequencies are now pi by t to minus pi by t. The cutoff frequencies would be, the value of that would be equal to omega c by t. If you have here omega c, now this becomes omega c by t. Omega c over t is your new cutoff frequency when you look at as if it is a when it is a continuous time signal in terms of that. So you could see here, in order to vary this cutoff frequency, you could either change omega c or capital T, and of course you could have changed both as well if that is required. So what it means is, one way of looking at it is, for example, I want to keep the same system without changing these cutoff frequencies. Still, I could get different a variable low pass filter with a varying cutoff frequencies by simply changing the sampling rate. And of course, I could have kept this sampling rate constant. And if I have a control over changing this omega c, that also I could have done. So both are possible, right? So that was the one. And then I gave you an example. You try it yourself. Again, this is a worked out example from the Openham and Scheffer textbook itself. So once you thoroughly try this out, okay, and arrive at some answer, you go through it and then carefully go through it and cross check your results with that. Okay, so that's as far as the first first part of today's today's meeting is concerned. So any questions so far in this part before we move on to the next part? Is everyone able to follow this? Let me just come back to again normal mode for a moment. Okay, so yeah, you are able to, any questions so far? Okay, so can I move go ahead for the second part? Yeah, I hope so. So I'm just moving on there. Right. So again, I'm sharing the screen and then going again back to this OneNote and this part. Okay. So this is another very important, part of the sampling, which you would very likely come across it probably at different points of time. Let me again take this pen. Spotlight. Okay. Right. So the question now is, see, this is also a very commonly encountered thing. You have a discrete time signal. You might have either obtained it by sampling a continuous time signal, or by nature itself it could be a discrete time signal, doesn't matter. Okay. So then usually when you are doing a discrete time processing through different modules, it is not uncommon that certain processing would be done at a specified values of sample rate. So for example, say 40 kilohertz, or there could be some restrictions on that. Okay, and sometimes even though there is no such restriction because of your computational issues, say you want to get some statistics of how your signal is. Uh, if you have a signal of very like sampled at a very small value of t, then getting that statistics, probably you might not require to do that computer statistics or all the samples, but you might be okay doing it after downsampling it by a factor 4 and then get the statistics. Assume that you are fine with it. Okay, this could very likely you could encounter in different stuff. Okay, so if that is the case, you want to do downsampling and upsampling within the discrete time signal. Okay, one possible way without looking at any new concepts, just based on what we studied so far, is you could use that x of n. Assume you know that for a moment. You assume that you know it by sampling at what rate you got this xc of t. Otherwise, also if you don't know it, also you could do some things, but doesn't matter at this point. So you can go to you can do a reconstruction filter, get back your continuous time signal, and from that you sample now at a rate that you want your x of the new discrete time signal you want it to be. Okay, so this way you could do and get this x1 of n, but this you almost never do it in practice for various reasons. But these are the three important reasons. One is reconstruction filter is never usually linear, so that would introduce certain problems. Analog to digital, digital to analog, in theory this is fine, but when it comes to practice, you have a lot of issues, but because of which you have various problems like quantization and other things, which we will not be going as such in detail in our course, in this current course. Okay, but there are a lot of problems there. Okay, so what you would rather like to do for this purpose is, if I give you a discrete time signal, if I tell you that I would like to downsample it by a factor m, okay, and giving me the new downsample signal x subscript d of n, which is nothing but you are taking, for example, your m is 4, you are capturing here every fourth sample or one sample in consecutive 4 values, you are picking one and constructing this ht of n. If I am doing that, I would like to answer different questions here. Like, if I know what is the frequency spectrum of x of n, can now tell me right away what would be the frequency spectrum of this, and how is this related to x of the DTFT of x of n. Okay, and then is there a limit on up to which I could downsample this so that I could still manage, but the signal is not aliased in the frequency domain for xd of n. Frequency domain aliasing is not there. Can I tell those limits? And suppose despite this a right away downsampling could result in aliasing, I am okay with losing some frequencies, but but still I want to downsample by that particular rate only. So what could I do? I'm okay with discarding the higher frequencies to the extent that it will avoid me the aliasing problem. So how to do that? So these are the things that are addressed in this lecture. Okay, before that, assume that the sampling period here is t. The moment you are downsampling it by m, it means its sampling period will be mt. So if you look at where the samples are placed in terms of capital omega s, this is 2 pi by t, right? And in terms of the omega s for this signal will be, of course, 2 pi by mt. And what is this value in terms of omega s? If I talk about small omega subscript s, what is this value on the left hand side? Hello, hope you could. Yeah, what is the value here? What would be? So hope I'm making sense. So for example, all I'm asking is, for example, if I ask you what is this omega s here, can you tell me?
2 pi.
2 pi, that's good. And what about this? Omega s dash.
2 pi by m.
Are you sure?
Here also it's 2 pi, sir.
Correct. Good. It's because the signal here you need to then multiply to this to get this is equal to 2 pi by mt is your omega s dash, right? This is getting multiplied with the time period here is mt here. So that would give you, this should make sense, okay? Because the discrete time Fourier transform has a periodicity of 2 pi. So the copy should get placed at 2 pi. Okay. So this is what would happen anyways. Okay. Let's come back here. So if you have not gone through it, maybe this sounds a bit faster, but again what I will do is either we should wait for one more class on Wednesday, but probably it is unfair for those who have already gone through it. So I would give a kind of a broad overview here. In any way, since I will upload this video, even if you are not understanding some bits and pieces in between, you just go back to the original video and then come back to this June session again. Okay. So let's start with xc of j omega. Assume that this is your continuous time Fourier transform frequency spectrum. Okay, the frequency spectrum of this. So the moment you are coming to the x of n, this is what the corresponding xs of j omega. This is like the frequency spectrum of a signal multiplied with an impulse train. What would happen there? This one will become 1 by t. Because of multiplying with the impulse train, copies are kept at multiples of 2 pi by t on both sides of the 0, right? This is what would happen. Now, this is the frequency spectrum of x of n. The only difference the moment you are coming from here to here is that just the omega would change now with multiplied with omega t. You have seen that copies would be placed at 2 pi, right? So then this would be, I'm calling it as a small omega n here, which is nothing but capital omega n multiplied with capital T. Okay, so that's your signal. Okay, for some like easy to follow up things, what I did is I also took here some relationships here. Okay, assume that your omega s is 4 times omega n. So this omega s t is chosen such a way that this is the gap is twice this omega n. Okay, so the whatever is till omega n, so 2 times omega n gap is there, then this omega n is there. Essentially, this is omega s and omega n. This distance is 4 omega n and 2 omega n is filled up. Okay, so then you figure out what would be the small omega n. Small omega n is nothing but capital omega n. Yeah, this you could see here. 2 pi by t is 4 omega n in other words, right? And from that you could figure out that omega n into t, this would be equivalent to pi by 2 minus pi by 2. Okay, even if you don't follow that, the simple way you could like reverse engineer this is, anyway the copy is at 2 pi, right? This gap is double the whatever it is this. Okay, so essentially this plus this should be this, so which means this has to be at pi by 2 and 3 pi by 2. That way also you could work it out. Now the another important thing now is to get the frequency spectrum for xt of e power j omega. See, right now we are not doing the mathematical part that we do in the last part of this one. So before that, easy to do things we are doing it. Actually, this is much easier to follow from the spectrum, plotting this spectrum. So look at it this way. Instead of sampling it by t, what would happen if I'm sampling it by 1 by mt? Okay. Now again, also we assume here your m equal to 2. Let's assume that. Okay, you are downsampling this signal by 2. Okay, so instead of taking samples at an interval of t, what would happen to the frequency spectrum when I take samples of that at 1 by 2t? Okay, that's what we are saying. So first easy thing, this would be 1 by mt or 1 by 2t, the magnitude part, right? And this one, if you had see for the same logic that we discussed there, okay, this would come now to pi here. Why is it so? That comes simply, yeah, this omega equal to omega n times t. If it is now this is omega n times 2t here, right, compared to this. So if it is earlier at pi by 2, now it should come to pi, right? Is it not? That's a straightforward extension from there. Okay, now we fixed. So then what would happen? The copies would always come at integer multiples of 2 pi. That's all. These are the only three things that we need to take into account. So we made instead of earlier 1 by t, but now your time period is empty. So this became 1 by mt. And then this omega n, whatever we have written is omega capital omega n times t. The t, that was pi by 2, but now it is 2t. So again multiply 2, that brings it to pi. Okay, so you have minus pi to pi. Now these copies are placed at when you look at from small omega, these copies would be placed at integer multiples of 2 pi. So this is what you would be getting, right? Hope this is clear. Then what you do is, then you try to figure out here, how could I get the same response from here to here, suppose I want to get. So what should I do? Yeah, first thing is 1 by t, 1 by mt is there. So you scale whatever is here by a factor 1 by m. That means, in other words, here this being 2, we are going to scale it by 1 by 2. First thing is done. Second, you want it at pi. Okay, you have it at pi by 2 to minus pi by 2 to pi by 2. So you do this x of e power j omega. This is what you are calling it. So you first make it to x of e power j omega by 2, so that it would stretch. Okay, now pay attention to those which are in green color here. That would bring the first copy is there from now minus pi to pi. Okay, when you are stretching, pay attention here, this also gets stretched. It's not only that. Okay, so when you are stretching that, this would, in fact, the gap would be there from pi to 3 pi. So the next copy would come there, then this 2 pi would become 4 pi. So you only have at the end of it these ones which are there in the green color. So, well, what else do we need? You need one more copy here. This is after all periodic with periodicity of 2 pi. So the whole thing, you need copies at omega minus 2 pi by 2 also. This should get repeated. Okay, so you could write it as 1 by 2 into x of e power j omega by 2 plus x of e power j times omega minus 2 pi by 2. Okay, this also should make sense to you from continuous time domain also. See, you are multiplying it to get a discrete time signal from a continuous time signal. You are multiplying it with the impulse time. Now the moment you are multiplying it, so here you made it t into 2t, right? So that means compared to that, you should have more copies here, right? So that means those missing would come here, right? So hope that is clear. Or otherwise, the place you are keeping the copies were earlier, yeah, compared to that, you should have additional copies here. So for example, we did it by 2. Suppose if I am doing it by 3, what would happen? In addition to the original copies, 2 more copies would come there. Okay, that's all. And then you want to avoid aliasing. How could you do that? Well, see here, if you call this value, whichever is there here, omega n, you are downsampling it by a factor of m. So where will this now go to? Omega n into m. So as long as this is less than pi or equal to pi, there is no aliasing here. So that means omega n times m is less than or equal to pi, which means your omega n should be less than or equal to pi by m. So you might be wondering, yeah, you could look at it depending on what exactly you are interested in. I might have written it to m less than or equal to pi by omega n as well. Suppose you don't want to play with omega n, but figure out an m that will not result in any aliasing, then this would tell you what m to choose. But if you are going to choose omega n, okay, such that for a given m you won't be having any aliasing, okay, that's also is possible. That means in that case, this would tell you your omega n, as long as is less than or equal to pi by m, there is no problem. Well, this omega n, do we have a control? Yeah, then it is not x of n that we would be choosing it. We make forcefully this cutoff, we apply a low pass filter and force the highest frequency to be not more than pi by m. This original signal omega n might be more than that, but this omega n tilde, if I call it, that we make sure that it is less than or equal to pi by m. You apply a low pass filter. What should be the limits here? Anyway, we don't want it to be more than pi by m. So omega c should be equal to pi by m. And on this signal, you will be doing the downsampling. Okay. So x of n is there, x tilde of n is there, and then you downsample x tilde of n, not x of n, and you get the output here. Okay. This is exactly, for example, take a look at here. This is already pi. If I had downsampled by a factor of 3 here, not 2, where will this go? Instead of going to pi, where will this go? If I had downsampled signal by a factor of 3, anyone?
3 pi by 2.
Very good. 3 pi by 2. So what should I do? This should be, so beyond pi, I should be applying this cutoff frequency and do the stuff there. Exactly. So there is from pi to 3 pi by 2, there is an overlap of things. Okay. So this, whichever, that relationship would come a little later. Okay. So that is where now you put a, so what could I do then? To do that, instead of having this pi by 2, if I apply a cutoff here, right, what should be, and then pi by m. Okay, pi by m is pi by 3. Okay, if I had a, yeah, anyway, I'm telling you the answer also for the next one in this part. Okay, so if you first apply a low pass filter having cutoff frequencies of instead of 90 degrees, at 60 degrees, beyond 60 degrees, okay, you don't keep it. So then what would happen? Pi by 3, downsampling it by 3 means that multiplied by 3, then it will come till 5. But of course, you will lose. You need to sacrifice something if you want to achieve whatever downsampling rate that you want to do. That will be, you prefer dropping the higher order frequencies. Okay, that's what this exactly tells you. And this exercise was exactly on the same thing. So you want to do it by m equal to 3. I already plotted here. So if I'm doing right away, how does this downsample version looks like? Exactly the same answer you told. So from pi by 2 to 3 pi by 2. Okay, there will be just like a pi by 2 to 3 pi by 2. Yeah, just take a look at there. Okay, you work it out again. M equal to 3. What would happen? What should be the cutoff frequencies here? If you apply this cutoff low pass filtering, you apply this low pass filtering on this. Okay, that result is, so multiplication of that with this, you plot it here, and after that on this, then you downsample this signal now by a factor 3. Okay, so that's the exercise for you. Yeah, this was the derivation for the same. You need to go through it a bit carefully. This is a slightly tricky thing. So if you are comfortable with summations, change of variables, when you have multiple copies, you find it fine. Otherwise, you pay a bit more attention here while you are going through it. Okay, the same theory, but in why you need to translate it to the equation appropriately. Okay, so for example, let me quickly go through it. X of e power j omega is 1 by t, k varying from minus infinity to plus infinity. Xc of, okay, I'm writing x of e power j omega in terms of xc. Okay, continuous time variable. So there is a scaling by a factor 1 by t above the amplitude. Omega becomes omega by t. Copies are placed at multiple intervals of 2 pi by t. But if I change this t to mt, what would happen? Instead of t here omega by t, I have omega by mt. And this 2 pi by t, instead of that I have 2 pi by mt. Yeah, variable r I considered here, instead of k I consider it r. So this will be r. Okay. Now what you need to do is this summation xd of e power j omega, you need to write it in terms of x of e power j omega. So if you pay attention, close attention here, in the first look, you might think, what, how does it matter? Each one is summation from minus infinity to plus infinity. But out of m copies here, when this is m plus I, that's ith copy would be same as this, if you closely pay attention here. Because in the denominator you have, it's like here you are getting 0, 1, 2, 3, 4. This is like getting 0, 1 by 4, 2 by 4, 3 by 4, and so on. Okay, this summations to be equal. You write it then r equal to I plus k m here, where this I varies from 0 to m minus 1. Okay, and when this is equivalent to 0, that is when for every m copies there is only one copy is exactly same. So while you are making summation of m terms here, out of that only one term would come out here essentially, because the denominator is bigger there. Okay, so to deal with that, you write it as I plus km, then you write it summation of this I varying from 0 to m minus 1 and inside 1, and that would exactly the same result which we have already seen graphically, right? So this would be compared to the original one, x of e power j omega. This will be amplitude will be scaled by 1 by m. Okay, if you compare with the continuous time signal, 1 by t is already done in x of e power j omega. So if you are coming from x of e power j omega to xd of e power j omega, only 1 by m scaling is required. And mi, so if you ignore 0, for example 0, you make I equal to 0, this is exactly equivalent to x of e power j omega by m, just the scaling in the omega axis. Okay, but we have already seen, in addition to that, m minus 1 more copies are added. Each copy is shifted by an integer multiple of 2 pi by m. That also we have seen in graphically why it should be so, we have already seen. So that the same thing we would be deriving here mathematically. So that's all this lecture. So we are done with then the downsampling of discrete time signals. Next class we would be going through the upsampling now of discrete time signals, followed by either in the same lecture or the other lecture where you have a rational, you want to downsample it by a value, let's say 1.5 times the original signal. How do you do that? So far we are dealing with either upsampling or downsampling by an integer value. So if you are doing it, let's say 1.5 times your original time duration, you want it 1.5 times t. How do you do that? That would be the subsequent lecture. Okay, with that we will even wrap up the sampling part with those two things. There are other things also, multi-rate sampling and other things, but I will, for the time being, I will not go through it. And after that we will move on to the DFT. That's the plan. Okay. You have 15 minutes of time around to have any clarifications if you have any questions. Yeah, means those who have not gone through the last two lectures might find it whatever I told is a bit fast, but I don't want to repeat the same thing here. Anyway, you have that lecture, so if you have not gone through it, first you go through it, and anyway then you, this is more of a summary or a broad view of that. So after that you come back to this Zoom lecture that I will be uploading there. Yeah, before that, any questions so far? I'll come back to the normal mode now. Or yeah, if you have any questions, I think this is better. So let me keep it this way only. So check me out. So if you, I think even if you are saying something in the chart, I might not be able to see. So just for a moment, let me check that out if I could. Yeah, let me move it a bit. Okay, because I don't know if you are saying something there. So I'm not sure if I could go back to the original mode. Okay, maybe then I stop share and come back. That's more convenient. Right. So any questions? Is that clear more or less? Yeah, here for the last part, for those of you who haven't gone through the video lectures, you might miss some things here and there. The detail you might be missing, but still you should be getting the overall picture. Okay, if that is not clear, then also feel free to yeah, get the doubts clarified. Any questions? Absolutely clear. Good. Then we are done in by 11:20 itself. So yeah, no questions at all. 100% clock kiए जाए. Good. Okay, fine, that's good. Okay, of course, if you have any questions still, you could always ask in the next lecture also, or drop me an email. I might be late in answering and replying, but you will get the reply for sure. Maybe just with some delay, but you are sure to get some reply. Okay, so good. So I don't think we require then any. Do you need a class on? Yeah, maybe then we will meet next week itself. Again on Monday. That would be, before that I would be making, if possible, the 2 video lectures. Okay, one lecture on the upsampling part. Then the other one is sampling by a non-integer value or a rational value. Okay, that's what I will do. And then with the next with the coming week, we will wrap up the sampling and we will move on to the TFT. Okay, right then. Yeah, I have something that's pending from my side is to give you some exercises that I will try to do it very soon. Within before the next session, you will also have those questions for you. Okay, so I'll stop here the video lecture recording, and as